So running a little late this morning. I apologize. Whoops. There we go. So we're going to talk more about entropy. Hopefully you guys had a chance to watch the video over the weekend. Okay. So entropy, kind of one of my favorite concepts, even though it's really, really difficult. And most of entropy involves calculus and stuff like that. But in this class, we're going to keep it fairly simple. Entropy is just chaos. It's disorder. Okay. And so we're going to talk more about entropy and disorder and how exactly that works. If a chemical reaction results in a higher amount of disorder, that is a favorable reaction. Okay, kind of like if a chemical reaction ends up giving off heat, that's also a favorable process. So we're going to talk more about both of those things and how they fit together in the rest of this unit. One of the questions you might get on the AP exam is something like, pick which one of these reactions would result in the greatest increase in entropy. Okay, which you should be able to do that fairly well, because there's just a couple of things you have to remember here. If you change state from a solid to a liquid or a liquid to a gas, then obviously that leads to an increase in chaos, right? This is kind of like a clean room versus a dirty room, right? So some of you, your rooms have a high degree of entropy, and some of you, they're a little more ordered, okay? But a solid, all the molecules are kind of in their place. It's very structured. They're vibrating a little bit, but there's not a lot of movement there. In a liquid, now the molecules are able to flow over one another. The movement is a little more random, a little more chaotic, okay? And by the time you get to a gas, it's just all over the place, okay? So that's kind of the idea there. Higher degree of entropy when you're talking about a gas. Entropy increases also as gas molecules spread out into a larger volume, because again, if you increase the possibilities, then you're increasing the entropy, okay? So if you increase the amount of space that the gas can travel in, then there's more probability of it being one place or another, and so that's going to increase your entropy as well. To decrease entropy, obviously, if you change state in the other direction, right? If you go from a gas to a liquid or a liquid to a solid, or any reaction that's going to lead to a decrease in the number of gas molecules. So the example here, we've got, at first glance, this might seem difficult to figure out what happens to the entropy here, and they might give you a reaction that looks kind of like this. But if you notice, there are 3 moles of gas here, or 3 molecules of gas on the reactant side. There are 2 molecules of gas on the product side, okay? So where on the reactant side you had 3 things that were all kind of moving in random directions, okay? So 3 things that you have to account for their probabilities of movement. On the product side, you only have 2 things, all right? So that's going to be a little bit less disordered because there are less things moving around. That kind of makes sense. So the less gas, the less molecules of gas you have, the less entropy. The more molecules of gas, the more entropy. And that's how you're going to tell when you have a reaction that's all gases. Okay, this kind of says what I just explained. Less freedom to move randomly because there are less overall molecules. And we call this degrees of freedom, okay? I don't know that we need to talk a lot about that. There's not really anything, I've never seen degrees of freedom on that AP exam, but just a little background information there in case you like chaos. There are 3 different types of motion a molecule can have. It can have translational motion, okay? So the entire molecule is moving in one direction. So obviously gases are going to have the highest degree of translational motion because that's just a molecule moving in a certain direction, okay? And so that's the more typical type of motion that we would probably think about when we're talking about chaos or entropy. Is the entire molecule going one way or another. There's also vibrational motion, okay? And the atoms within a molecule typically vibrate, kind of back and forth. They get a little bit closer, they get a little bit further away, okay? And I know we talked about this last year. I don't know if we've mentioned it a lot this year. But these molecules within themselves are always vibrating just a little bit, okay? And there's also rotational motion. These things can spin, okay? And so those are the 3 types of motion that we usually talk about when we're talking about the movement of a molecule. It can be vibrating, it can be rotating, or it can just be moving in a straight line one direction or another. The more energy a molecule has, the more entropy it has. Okay, kind of makes sense, right? If a molecule's moving faster, its movement is a little more random. It's vibrating a little bit faster. It's probably rotating a little bit more. So increasing the temperature increases the entropy. And I'll bet you could have guessed that if I had just asked you that, because it just kind of makes sense, right? You heat something up, the entropy increases. So even if you have a solid and you heat it up but not quite to its melting point, so it's still a solid, you're still increasing the entropy just a little bit. Okay, if you have a gas, even though you're not changing it to a new state of matter when you heat it up, you are increasing its entropy because you're increasing the speed those molecules are moving. So decreasing the temperature decreases the entropy, of course. And then we've talked about absolute zero before, so I think you guys know that. But the reason it's absolute zero is because it's that theoretical point where all motion stops. Rotational, vibrational, translational, it all stops. Okay. At absolute zero, just by definition, this molecule is in a state of perfect order. In other words, there is no disorder in that system. So you want complete order, get to absolute zero, okay? Otherwise, there's going to be disorder in the universe. So this is actually the third law of thermodynamics. Second law we talked about last time is basically just that the disorder in the universe is increasing over time, okay? And then the third law is that when you have something at absolute zero, that's when its entropy is zero. Okay. All right. So here's the entropy curve of a substance. And notice this is kind of exactly backwards from the heating curves that we did in, I guess it was chapter 5. In the heating curves that we did in the book, what happened was this thing would, I'm going to erase this after I drop it, this thing would heat up for a little while, and then as its phase changing, it would completely flatten out, right? Because we were talking about how the temperature changes, and it stopped changing at a certain point, and then it would raise for a little while, and then as we were having the phase change, it would flatten out. This does kind of the opposite of that. At the phase change, you have this steep, sharp increase in entropy right at that point, okay? So is there a question on your... Yeah. Why is there a sharp increase in entropy as the substance goes from a solid to a liquid and a liquid to a gas? Why is it that there's this huge jump in entropy right at that point? Okay, so there's actually this point right here where this thing melts, where all of a sudden these molecules have a much greater degree of freedom, right? They are much more easily able to move around, and their movement becomes much more random. Okay, so the entropy increases a little bit as you increase the temperature, but those phase changes, that's what really, really increases the entropy, because now these molecules are much freer to move around. Okay? Hopefully that makes sense. You can put that in your own words. Again, I'm trying to go pretty fast today. So, summary here, entropy will increase when you have liquids or solution. Okay, we didn't talk about that. We talked about this yesterday. Not yesterday, but whenever you watched the video. If you put a solid into a solution and it dissociates, that also increases the disorder of the system. Okay, and we didn't really talk about that today, but you can sort of consider that to be a phase change to some extent. So when you take a solid and you either melt it, turn it into a liquid, or you put it into water and it dissociates, that's going to increase the entropy. Okay, if you form a gas from solids or liquids, that's definitely going to increase the entropy of the system. And if the number of molecules of gas increases during a chemical reaction, those would be the three ways that the main ways that you'd be looking for when you're talking about an increase in entropy. Okay. Whoops. Oh man, not doing well this morning. Everyone saw that, but we can talk about why. Let me go ahead and erase all the other stuff that I need to erase here this morning, because evidently it's all on here. Yeah, we're getting back to delta H, sorry. That was not what I wanted to do. Come on. See, I should just pause the video for a second while I'm doing this, because everyone's looking at the these now. Seriously, I don't know why I thought it was a good idea last year to save all of this stuff. Oh, you know what I think I was doing? I think I was posting the filled out notes on Moodle, so I think that's why I did that. Alright, anyway, back to this. Nope. This is going to happen again. I'm going to save it. There we go. Alright, so we want to just look at each of these pairs and decide which of these has the greater entropy. And again, this should be fairly simple, even without having already seen the answers. It says explain your choice. We're going to talk about that, and you can decide whether you want to write it or not, but I'm going to go through these fairly quickly because I think most of them are going to be fairly self-evident here. Out of the first pair, the mole of NaCl or a mole of HCl, which one is going to have the greatest entropy there? Okay, the gas, right? Does that make sense? So the gas is going to have more entropy than the solid. That one's fairly obvious. B, 2 moles of HCl gas or 1 mole of HCl gas. What do we think? Okay, more molecules, more chances for randomness there. Okay, so that's going to be our choice on that one. Does everyone understand that? Because that one we didn't specifically talk about just amount of gas. I guess we sort of did with the number of molecules. Okay, 1 mole of HCl gas or 1 mole of argon gas. Interesting. What do we think on that one? One mole of HCl gas or 1 mole of argon gas at 25 degrees Celsius. See, I feel like I threw some examples at you we didn't really even talk about. Did you talk about that one? Molecules. Temperature. Oh yeah, we did. Okay. Here's our key on this one. I forgot. Vibrational motion. Okay? So let's look back over here. This one's kind of tricky. Which one of these has vibrational motion? The HCl, because that's the one that has a bond, right? The argon is just kind of by itself. It's just an atom, okay? So because this one has a higher degree of movement because of its vibrational motion, that one's going to be a little bit more chaotic or a little bit higher entropy, okay? And then 1 mole of N2 at 24K or 1 mole of N2 at 298K. Again, hopefully fairly evident on that one, right? The higher temperature. Okay, so not too hard, right? Does that make sense? And this is, I kind of like entropy. It's not too bad. And then another type of problem, predict whether the entropy change of the system in each of the following isothermal reactions is positive or negative. What does isothermal mean? What does iso mean? The same, right? Okay, and what is thermal? Sounds like heat, right? So we're probably at the same temperature for the entire reaction. That's all that means. It's just, yeah, every once in a while they'll throw terms like this on the AP exam and you have to know isothermal. Just don't be intimidated by their big words, okay? All they mean is same temperature. So CaCO3 changing into CaO and CO2. What do we think? Increase or decrease in entropy there? Okay, there's a gas on the product side, so that's going to definitely be an increase in entropy. What about B? Okay, yeah, this one's a little bit trickier because they're all gases, right? But we've got 4 moles of gas, or 4 molecules, on the left side, and then we've only got 2 on the right side, so that's going to be a little bit of a decrease in entropy. Those molecules are going to be a little less free to move around. What about N2 plus O2 gives you 2NO? Okay, yeah, you have already seen the answer, haven't you? Alright, so just based on this information, we really can't determine that, right? You can't say that for sure that it's going to be the same at the end because there might be something else that we haven't considered here, but based on the rules I just told you, we can't figure that out because it's the same number of moles of gas on each side. These are all bonded, so there's vibrational motion happening on each of these, okay? And so it's really hard to tell based on what we know, whether or not that would increase or decrease. Okay, so they're not going to throw one like this onto an AP exam and ask you, does it increase or decrease, unless they give you some additional information that would help you. Okay. All right. Just heading. Just entropy changes. Yeah. So absolute entropy. This is a little bit different than H, right? With H, we had trouble determining like an absolute heat content of something, okay? But here, scientists actually can determine the absolute entropy of substances, and that has to do with the fact that we know that at 0 Kelvin, the entropy of a substance is 0. So you kind of have a starting point there, okay? But you have to do some fairly complicated calculus to figure these out, so let's just let the scientists figure that out. So usually these values are reported as standard molar entropies, okay, which is S degrees. You guys remember seeing the that? The heat of formation of certain things, okay? So this is very similar to that idea, in that you're just given some values, and then when you have an equation, you can, subtract the products from the reactants. Take the products minus the reactants, okay? So subtract the reactants from the products. And you can figure out your overall delta S for the reaction, okay? So we're going to do some review in class today on how to do delta H type problems like that, because I think reviewing on that will help you with this, okay? So some things to know about the standard molar entropies. Sorry, I'm getting an announcement. All right. So enthalpies of formation, unlike enthalpies of formation. Now, when I say enthalpy, do you guys remember what I'm talking about? Enthalpy is delta H, okay? All right, or just H, I guess. Entropy is S, so you got to keep enthalpy and entropy straight. I don't know why they made those words so close to one another, but they did. So just watch out for that, okay? Enthalpy, we're talking delta H. Entropy, we're talking S. So unlike enthalpies of formation, standard molar entropies of elements at the reference temp are not 0, okay? These things at 298 K are going to have some disorder to them, right? When are they 0? At absolute 0 Kelvin, okay? Standard molar enthalpies of gases are greater than those of liquids and solids. That kind of makes sense. Standard molar entropies, wait, did I do that wrong? Standard molar enthalpies of gases are greater than those of liquids and solids. Why am I talking about enthalpies? I may have messed that up. Maybe that's supposed to be entropies. Yeah, I think it's probably supposed to be entropies there, because that's what we're talking about. I don't know why I would have said that in the midst of this. Standard molar entropies usually increase with increasing molar mass. I'm just going to go ahead and change this, because it makes sense, You're going to have a greater entropy when you have a gas than when you have a liquid or a solid. Standard molar entropies generally increase with increasing molar mass, okay? The bigger the molecule, typically the more disorder there is, because within the molecule itself, now you've got more moving parts. You've got more protons, you've got more electrons. So that, just the more you have, the bigger it is, the more chaos there is usually in that system, okay? Standard molar entropies generally increase with an increasing number of atoms in the formula of the substance, okay? So, and again, that's kind of because of that vibrational motion that happens. So the more atoms you have in the molecule itself, the more motion is taking place between the atoms, and that's when you get higher entropy. Okay, so here's the equation for entropy. Delta S equals the sum of S of the products minus the sum of S of the reactants. And the N and the M, do you guys remember what those stand for? Because this is very similar to the equation that we had for delta H. They stand for the coefficients in the equation, okay? Oh, yeah, it does say that. I should look at my notes before I ask a dozen questions. So N and M are the coefficients in the chemical equation, all right? Hang on just 1 second here. Okay. So, sample problem here, calculate delta S degrees for the synthesis of ammonia from N2 and H2 at 298 K. And the thing that I forgot to give you guys again was any of the entropies, the standard entropies that you would need for this. So let me find them real quick. I'll put them on here. I think there's a chart in the book on page 753. Okay, so that would help us out with this. So the standard entropy for N2 gas is going to be 191.6. I'll just write these down below them. 198.6, or so 191.6 joules per mole times Kelvin. Okay, and then the H2 is going to be 130.7. Make sure these are gases. Yeah, they are. And again, that is joules per mole times Kelvin. And then the NH3 gas is 192.5. So if they gave you a question like this on an AP exam or on my test, I would give you these S values, just like I gave you the delta H formation values when we took that test. Okay? So then you just have to take the products minus the reactants, and don't forget to multiply by the coefficients, right? So this is our product, the NH3, so we take the 192.5 joules per mole times Kelvin, and we multiply that by 2. We have been in the habit for a long time now with equilibrium of squaring things when they have a coefficient of 2. Don't square this, just multiply it by 2, okay? I know that's confusing, but just gotta remember that. And I'll put this whole thing in brackets because there's your products, and minus the reactants. Now the N2, there's only one of those, so it's just 191.6 joules per mole times Kelvin plus the H2, which is 130.7 joules per mole times Kelvin times 3. So there's a coefficient 3 in front of it. That's supposed to be a 3. There we go. All right. So once you work all that out, that should give you your delta S for this reaction. Okay, and I'm getting a delta S here. And again, this degree thing, just to remind you, all that means is we're at 298 Kelvin, or 25 degrees Celsius, okay? That's all that little circle there means. It just means at standard temperature, okay? So I'm getting a delta S of negative 198.7. Again, that's joules per mole times Kelvin for the units. That's going to be your units for S. What is that telling us about this reaction? Say that again. Well, okay, that if we were having a delta H there, that would be exothermic, right? What is this telling us about the entropy change? It's actually decreasing. It's becoming a little more ordered, right? Okay, does that make sense? And you got to think about it a little bit opposite from delta H, okay? So the more positive it is, the more disordered it is becoming. The more negative it is, the more ordered it is becoming, okay? So this right here is not necessarily a favorable change. It doesn't seem like it at first glance here, because, you know, this is getting more ordered, okay? Which is not the way that the universe tends to go, okay? But the thing is, if this becomes more disordered, but the surroundings, or I'm sorry, if this becomes more ordered, but the surroundings become even more disordered, so that the overall entropy change is greater than 0, then this might still happen spontaneously, okay? So, change in entropy of the surroundings depends on how much heat is absorbed or given off by the system. So we need to figure out the entropy of the surroundings. What we just figured out is the entropy of the system itself, okay? I don't know if you guys remember this from the video over the weekend, but when I say delta S from now on, we're thinking in terms of the system, if I don't specify, okay? So now what we want to do is figure out the entropy change in the surroundings, and that's going to depend on how much heat is given off by the reaction, okay? Because the amount of heat absorbed or given off, that's going to determine, you know, like how more ordered or disordered did we make the surroundings. If we heat up the surroundings, what are we going to do to the entropy? If we make the surroundings warmer, what does that do? It increases the entropy of the surrounding area, right? Now, if we decrease the temperature because we're absorbing heat into the reaction, then that's going to actually decrease the disorder of the surroundings as well, okay? Probably not going to happen that way, because usually in any of these processes, delta S is going to be greater than 0 for the entire universe, okay? So our formula for finding entropy at constant temperature, we talked about this last time, the Q rev over T, okay? Now the thing is, this equation actually works for any reaction that's held at a constant temperature. So you could say your delta H over T as well for this one, okay? So we want to find the entropy change for the surroundings in the NH3 reaction we just did. So we need to calculate the heat gained or lost by the surroundings. Now again, in a very unhelpful, oh no, I actually did give it to you on this one. Okay, so the delta H formation for the NH3 here is negative 46.19 kilojoules per mole. So what is the heat change overall for this reaction? It's not negative 46.19. I'll tell you that. Look back at the reaction for a second. How many moles of NH3 are we making in this reaction? Okay, so what do we need to do with this delta H here? So either divide by 2 or multiply by 2, right? Okay, this is how many kilojoules per mole, right? Since we have 2 moles, we need to multiply by 2, okay? So negative 92.38 kilojoules. That's our delta H for this reaction, okay? So now we can calculate the delta S of the surroundings. Now, the other thing that we have to be careful with here, when we found our delta S over here of the system, we found it in terms of joules, right? So we should probably change this delta H here to joules, okay? So how many joules is this? You say lots? Yeah, it's lots. 92,380 joules, okay? Now we can calculate the delta S of the surround. Oh, wait, what am I doing? That's not right. I was jumping ahead here. So the delta S of the surroundings is going to be negative 92,380 joules divided by the temperature at which this is happening. Which, what do we say about that little degree sign there? It means it's at 298 Kelvin, 25 degrees Celsius. Okay. Of course, we want to be working with absolute temperature here. And technically, this is now, you know, this is joules per mole again, just because, you know, well, maybe I don't want to say that just yet. Okay, so negative 92,380 divided by the 298K, that gives us an entropy change of negative 310 joules. And again, because this is entropy, joules per mole times Kelvin would be our units here. Maybe I should put per mole here, because then it makes sense when we actually divide it. So we do have to be careful with our sign here, okay? And here's where we can get a little bit off if we're not paying attention. We figured out the delta H of the reaction itself, right? But we're wanting to calculate the delta S of the surroundings, okay? So if the reaction is giving off that much heat, that means the surroundings are absorbing that much heat. Does that make sense? Okay. So with respect to the surroundings, this is actually a positive heat change, which makes this a positive delta S. Okay. Everybody okay with that? I mean, you kind of have to watch for that. It's really easy to miss that. Okay, so we just figured out the entropy change of our surroundings. Now let's compare that to the entropy change of our system. Which one's bigger? Surroundings, right? So then we can go back to what we did on the last set of notes. The delta S of the universe is the delta S of the system plus the delta S of the surroundings. Okay? Delta S of our system is negative 198.7. And we're going to add that to the delta S of our surroundings, which we just calculated as 310. Okay, so what that tells me is the overall entropy change in the entire universe. Probably so. 111.3 joules per mole times Kelvin, okay? And actually, it tells us this reaction is spontaneous, but it is just barely. So what that means is this reaction happens very, 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 very slowly over time, unless you do something to speed it up. And we actually talked about this reaction before. You guys remember what the special name for this reaction is? Or the process that speeds up this reaction? Yeah, I mean, that's what you do, and you do it at a certain temperature and pressure. It's called the Haber process, okay? And it's a very important process for producing ammonia. So, okay, that's it for today.